9D, the graph of the gradient or derivative function. The derivative graph is simply being able to plot on what the gradient is at every point according to the x-axis. So if we were to draw a graph over here of what the axes would look like, you can see that this would be split up into three parts if this were between x and between dy by dx. So we're no longer graphing between x and the values of y, but x and the gradient. So this section over here is going to be where my gradient is positive. On the x-axis is going to be when my gradient is 0, and below my x-axis is going to be where the gradient is negative. Obviously, the closer that we get to the x-axis, it means that my gradient is becoming more and more shallow because it's approaching a gradient of 0. And when it is leaving the x-axis, so whether that's in the positive or the negative direction, it means it's becoming more steep, which means the gradient is becoming more and more positive or more and more negative. We would see that generally when we are stepping away from the graph, away from a turning point. So if here we have a turning point, the further that we go away, the more and more steep that my graph becomes, whether that's in the positive direction or the negative direction. In order to draw the derivative graph, you just need to find out where are your stationary points, in which case you'll plot them along the x-axis, that's your step one. At which points do you have a positive gradient, and at which points do you have a negative gradient, and plot them on the corresponding axis. So that there is your step two. Just note that if the derivative does not exist at a particular point, what you can do is use an open circle on the graph. So if if it's undefined at 0, we can use an open circle and continue from there. Let's practice this now with example 8. So what you can see here is you've got a quadratic. The function is x squared minus 4x plus 3. And because we've got the function, then we can actually find the rule of the derivative and graph it from there. But you're not always given the function. Sometimes you'll be given a graph without the rule, and you'll need to be able to draw this graph on. Now, when I'm looking at this graph, I can actually analyze the three parts to it. So you can see this analysis over here. When x is equal to 2, so that's at this point, we can see that the gradient is 0. So my gradient is flat. When x is less than 2, so for all of the points where it's less than 2, you can see that I've got a negative gradient. It's quite steep and it slowly approaches 0. So that is going to approach my x-axis on my derivative graph. Then I can see that when x is greater than 2, it is becoming more and more positive. So when x is greater than 2, it starts off very shallow and it becomes more and more steep, moving away on the positive section of my gradient axis. So what would this look like as a graph? Well, if I were to put in a pair of axes, remembering that your step one is always starting off with your stationary point, which in this case is at x is equal to 2. We know that that's at 0, so should have labeled the axes first, x and then dy by dx. Before x is 2, as we established, it is negative, so we will be starting at the point 0, so it's quite shallow, and then it becomes more and more negative as we move along, and same thing happens in the positive section. So starting at 0 when x is 2, and then becoming more and more positive. Because I have my specific rule, I can also find this point at which it crosses the gradient axis, but because it's not the y-intercept, it's a gradient intercept, it doesn't actually mean anything to us. So you don't really need to find that point because it's not going to contribute anything. The key point that you must label all the time is this over here. So yes, it is our x-intercept on our derivative graph. More importantly, that means that it is our stationary point, which in this case is 2, and the gradient is 0. You can see that if we were to plot the graph on a CAS calculator, you would end up with what we have just before. This is a very similar example, as you can see. It is a quadratic, so let's work through the steps once again. We can see that we have our stationary point at x is equal to 1. That is the most important step. Before x is equal to 1, what we can see is that we have a positive gradient. It starts off quite steep, becomes more shallow, and then after x is equal to 1, it becomes more and more negative. So it starts off quite shallow and becomes more steep. Now let's translate each of these three steps. We have established that when x is equal to 1, we have our stationary point. Beforehand, we are at a positive gradient. So we are starting off quite positive down here, quite steep, and then we sort of start to shallow off until we hit zero. So quite steep, positive, and then we approach zero. And then you can see we start off quite shallow and become more and more steep in the negative direction. So that means we're starting off with a smaller negative number as we are shallow and become more and more negative with a larger negative number or gradient. This is what it looks like. Because you'd need the actual rule to be able to graph it on a CAS calculator, we'd have the rule for the derivative function, which is why then they would know that the intercept is at 1. But again, this is not an important value and a value that you won't need to find. I thought we'd also do one more example with a non-quadratic graph. So this graph over here, whether you can recognize what power it might be or not, it's not really relevant at the moment because we should be able to look at any graph and be able to draw the derivative graph from it. So first thing, we will start off with our stationary points. So you can see we have 2 stationary points. The other thing you might notice about this graph is it doesn't actually have any x values, which is often the scenario that you'll be given. So we're just going to be able to match where these points lie onto our new axis. So before I even continue analyzing, I can start drawing my derivative graph using the points that I found. So the first point that I found, which is my stationary point, I can see that one of them very clearly happens at 0, so that's quite easy to label. I don't know where the other one happens, but it happens at approximately this x value over here. So we will put in our stationary point there. Let's have a look at what happens before that x value. I can see that that gradient there is negative. Starts off quite steep, so it's going to be away from my 0 point, and it becomes more shallow approaching that point. Notice that because this is not a quadratic, we're not actually going to result in a line for my derivative. So it's going to be a little bit curved still. So quite negative and approaching that point there. Now my second part is what happens in between these 2 stationary points. Well, first of all, my gradient I can see is positive. It starts off quite shallow, becomes steep, but then it shallows off again. And so if I follow that idea, it starts off quite shallow, which means it's a small gradient, small positive, becomes a greater positive gradient, but then it shallows off again until it hits a 0 gradient once again. And then if we have a look at what happens after 0, it's still a positive gradient starting off quite shallow and becoming more steep. So a small y value and becoming a larger y value. You can see that at the point of inflection, it's going to result in my gradient remaining in the positive section of my derivative graph. If you initially notice that this in fact is a quartic, when you differentiate a quartic, so a graph that is to the power of 4, I will end up with a cubic graph, an x to the power of 3, which is what we have over here.